All right, I continued reading Fire in California's Ecosystems this morning, and I only got about 2 pages into the first chapter just because it was so jam-packed with interesting information, and thought I'd just try to share what I learned so far in this chapter. So what I was talking about was how California's bioregions and vegetation has evolved over time, depending on geologic upheavals and climate change. The plants adapt and migrate depending on the climate and the geology around it. So, just an example here, 50 million years ago, California was actually apparently low-lying, so not as mountainous. And then it was also much warmer than we are today, so it had almost a tropical climate. And this book was saying that we had plants and trees that you would see in southern Mexico or East Asia. And then around 15 to 17 million years ago, it was the warmest time that it's been in the last 23 million years. So because of this, the plants in California adapted to this, and there was a lot of variation from west to east. So the plants along the coastline were very different from the plants inland. And that makes a lot of sense because anytime there's warming or cooling, the plants and the plant communities along the coast aren't going to change as much because they'll be moderated because the ocean temperatures don't change as much as land temperatures do. And then the air over the ocean kind of moderates the air of your coastal communities. So those communities on the coast would be a bit more moderated than the inland ones that would be seeing the warmest temperatures that they've had in 23 million years. Now then it goes on to say that about 7 million years ago, we had a pretty similar climate to what we have today. It was kind of Mediterranean. We started seeing some grasslands, some chaparral, I believe it said some pine forests up in the mountains. But then and at this time, we started seeing a lot more what you'd call geologic upheaval. So our mountains were getting a lot taller, whether you're talking about the Sierra or the Klamath Mountains or the Transverse Range. And then that has a pretty interesting impact on your plant communities as well. And you can think about if you have flat land with the same climate, all those plants are going to be very similar. But then all you have to do is put a mountain in there, and then all of a sudden you introduce the rain shadow effect. So on the western side of the mountain, or the windward side, you're going to have that rising air, and then as that air rises, it's going to cool down. As it cools down, it can't hold as much water vapor, so you produce a lot of clouds, and then just like squeezing a sponge, you get a lot of rainfall on the western side of the mountains, and then your plants would adapt to that increase in rainfall. Now the opposite happens on the eastern side of the mountains. Since that air was squeezed out on the western side, by the time it goes down the eastern side, there's no more moisture in it. Or there's maybe some, but not as much. So then as it descends, it's going to also get warmer and drier. So then you end up with deserts on the eastern side. And you can see examples of this all over. Santa Cruz Mountains, which is on the windward side of the Central Coast, has a lot more rainfall than San Jose, which is on the leeward side. So take flat land, you have very uniform plant compositions, throw a mountain range in there, and all of a sudden you have all this variability that you didn't have before. Just a very interesting example of how plants, climate, and geology can all kind of interconnect with each other. And I'll connect this with fire eventually, but want to just continue going through this timeline. So then it goes on to say that I believe about 2.3 million years ago to 10,000 years ago, we had a period of ice ages. And then you can imagine the impact that had on our plant communities. And I wonder if this is the ice age that kind of carved out Yosemite as it was retreating. I believe that's why Half Dome is as flat as it is. It was where a glacier just scraped the side of a mountain in half. So 10,000 years ago, the glaciers retreat, and we enter what's called the Holocene, which is, I believe, a very similar climate to what we have today. And there's still some warming and cooling here and there. And you can imagine what your plant communities are doing while this happens. When it gets warmer, your plants are going to move north. So like Southern California plants moving up to Northern California. When it gets colder, your plant communities move south. So maybe some Canadian forest moves down to, Northern California. Southern California, that would be a bigger difference there. So it's just talking about how this is all very connected. And then you can also think about the impact that this would have on wildfire. So I'm talking about millions and thousands of years ago. So this is before humans are starting tons of fires, at least in California. So your fire frequency would be mostly dependent on things like lightning. And then that would change depending on geology. So you usually get more lightning up in the higher elevations. So as you throw more mountains up in California 7 million years ago, you probably increase the amount of lightning, increases the fire frequency there. But overall, the introduction of humans is going to create much more changes in your fire frequency and over a much shorter period of time than anything in the past. Now, the main thing that this book was talking about was the impact that fire also has on the evolution of plants. And it does bring up a pretty important point where it's, if you're in California and you want to take care of some plant community or some ecosystem or even some animals out there, fire has played such an important role in our ecosystem and the evolution of these plants that you kind of have to understand how fire impacts these plants to actually know how to take care of these plants. Just for example, you might think in the giant sequoia forest, you might think, oh, we want to protect the giant sequoias, so let's not have any fire up there whatsoever. However, giant sequoias have evolved for thousands of years to live with fire, and it actually helps them. They're I believe it's called a pyrogenic species, where they not only live with fire, but they require it in their survival and reproduction. So if you want to protect the giant sequoias, it might be tempting to say, okay, let's eliminate all fire. But then you realize that if you eliminate all fire, all of a sudden you have all these fuels building up. And then when a fire comes through there, it can be so intense that it overwhelms the giant sequoia's natural defenses. And that's the key word right there, natural defenses. That's where I'm talking about how the giant sequoias evolved with fire. Just some cool examples here. Their bark is fire resistant. It has something called tannin in it. So a small fire can come through, clear out some of the other plants that maybe are competing with the giant sequoia for resources. It can clear that out, but then the giant sequoia is fine because it has this fire resistant bark. The other thing it does is it engages in self-pruning. So this is where it drops all of its lower branches so that, again, when a small fire comes through, the giant sequoia's canopy doesn't catch on fire. It just goes around the fire-resistant bark. And then finally, the giant sequoia will drop serotinous cones. So that's a cone that is like sealed shut until a fire comes through, and that almost kind of like springs the cone into action. And you can imagine why the giant sequoia evolved this way with fire. Fire comes through, clears out all the other competing vegetation. All of a sudden you just have some bare soil, much more access to rainfall and sunlight, and then that seed is springing to life at just the perfect time because there's so much less competition, makes it much more likely that it turns into an adult giant sequoia. So pretty interesting there. But then going further into the nuance, so you might think, okay, so in an environment, you want to have fire to promote the species that have been living with fire. But then it gets even more complicated because the forests, like giant sequoia, could be completely different than the chaparral on the central coast. And that ties in with the fire frequency. So for example, up in the Sierra, they have a lot of thunderstorms, a lot of lightning, it's higher elevation. So your fire return interval might be every 10 years. So the plants have evolved to every 10 years there's a fire. So then it's it's built up not only the structure of the plant itself, but how it reproduces to kind of live in tune with that fire frequency. Whereas the chaparral on the Central Coast has the lowest frequency of lightning in the United States. So the last thing you would want to do is go in there and do a bunch of prescribed fire every 5 years or 10 years, because that's not what the chaparral evolved with. The chaparral evolved over thousands of years to a fire interval of maybe 30 years or 50 years or 100 years. So while the chaparral has also evolved with fire, it has plants that require fire for germinating its seeds or clearing out competition. Or one example is I believe it's chamise, a lot of chaparral plants. The entire top of it can burn off, but then it has a burl underground, which is just like a store or a bank of resources. And then when the fire comes through, a lot of the competition's cleared out, that burl can sprout like new branches and kind of regrow the old plant from kind of its reserves. But where this ties in with kind of the point I'm trying to make here is those reserves were built up over a fire frequency of maybe 50 years. So if a fire comes through and the plants, you'd think it's destroyed, but it really has its burl underground and it sprouts back up, it's ready to go again. And then you think, okay, it's been another 5 years, let's do another prescribed fire. And then you burn it out. Well, it used all of its reserves and it wasn't able to build its reserves back up or create its seed bank that it needs, because it evolved to do that over a 50-year time span. So then if you come back in and do another fire 5 years later, hasn't built up its reserves in its burl, it hasn't built up its seed bank within the soil, and then all of a sudden you kill that plant, which is adapted to fire, but at a different interval. So main point I'm trying to make here is that this is how plants evolve with climate, with geology, and with fire is very complex. And that's why I'm going to continue reading this book, hopefully past page 2, to try to figure out a lot more about this very interesting topic. If you want to learn more, you can join this little journey with me, and thanks for watching.